All right. You guys can hear me, right? All right. I see some yeses. All right. So remember, there's three pieces of information in an NMR spectrum. We already talked about. We left out set number 2, correct? Set number 2. I think we're on number 2. We're on lecture number 2. Yeah. Yeah, there's three pieces of information, right? There's integration, which we talked about, which is the area under the curve, and it's essentially the number of protons. It's the relative number of protons, right, under each of the signals. And then there's chemical shift, which is different. Chemical shift is just the position on the x-axis, and that is more like the chemical environment around the proton, we'll say. Like, it's the chemical environment, or like the type of proton in a molecule. Okay. There's going to be a third thing, and that's called splitting, and that's going to be the basically what that'll be is something with a neighboring environment. It's like that's what we'll see that today. It's like, is a CH2 next to a CH3, or things like that. It's like the connectivity between protons. So given those three things, we can really figure out chemical structure really well. Okay. So we already introduced chemical shift. Again, it's just the position on the x-axis relative to TMS, which is tetramethylsilane, and that is it's kind of like the 0 point. Early on, people discovered TMS and said, it's going to be a 0 point in NMR. So everything's always relative to TMS. Remember, the x-axis can be measured in hertz, but that's not very useful. And it's better if you can normalize it into a different units that are universal between NMR machines. And that's what we said. So because hertz varies between NMR machines and magnet sizes, right? And these different size magnets have a different meaning of hertz, right? So it's better if we have a universal measure of the x-axis. Okay. And so yeah, hertz is bad because it's dependent on the spectrometer frequency. So we have this thing called chemical shift, and you don't have to calculate this, you don't have to know the formula, but it basically converts hertz into a universal scale on the x-axis. And it's called ppm, parts per million. It's the universal measurement of chemical shift. And so now we have this universal scale, and that's great because, if I say my peak's at 3 ppm, it'll be at 3 ppm on any NMR machine in the entire world because it's a universal scale. Okay, and then also, yeah, the meaning of a ppm, like if I say like 1 to 2 ppm, that actually I mean, depending on the machine, the spectrometer frequency of the machine, that actually has a different meaning of hertz. Of course, that makes sense because hertz depends on the operating frequency of the NMR machine. Okay, so 1 ppm on a 60 megahertz machine means 60 hertz of space. And on these greater frequency NMRs, it's actually a larger amount of hertz. So more information can be encoded in this space. Okay, and that's the purpose we would, like, at SF State, we have a 500 megahertz NMR. We have 2 of them, actually. Those are $500,000. You might be able to buy a 60 megahertz NMR on eBay for a couple $1,000s. If you really want your own NMR, you maybe $10,000, I don't know. But like, these are so old and very, very kind of obsolete 60 megahertz NMRs. Okay, good. All right, so we showed these charts. We introduced the charts of NMR shifts, and these will be useful as we go along. This is a very great simple one. You know, it just breaks down the NMR, the proton NMR spectrum into a couple little slots. And we're going to see examples of these different things. This is usually what I give you on the exams. It's sufficient to solve almost any NMR problem. Don't have to memorize it, but knowing the general areas, and you know, you'll just start recognizing, like, oh, benzenes are around 7, for example. You'll just start learning that. And the other ones I maybe commit to memory are the 3 to 4 range, which is if it's next to an electronegative atom. Let's like a CH next to a Cl, or a CH next to an oxygen, those kind of things. And also the 2 to 3 range, which is next to a pi bond. So yeah, those ones we're just going to see a bunch very shortly. This is another correlation chart. It looks a little more complicated, and it is. It's, you know, it just provides a little more detail, but the detail is not necessarily helpful. So if you look on the web, there's probably 1,000 different ways of showing this chart. The one I just showed, I think, is probably the most sufficient for this course. But yeah, you can break down the range of signals very, you know, precisely, but it's actually maybe less useful than just a simple chart that I just showed. Okay, so why does deshielding occur? And what does deshielding mean? Left or right? Signals go to the left or right when you deshield? So it's left, right? So deshielding means to the left of the NMR machine, right? And so why does that happen? And I already gave you a hint. There's kind of 2 situations that I'm going to talk about. This is the first one. All right, remember what I said about, like, if I have valence electrons around the CH, and let's ignore the chlorine right now, just pretend the chlorine's not there. What did we say that the valence electrons do to the magnetic field? We said it shielded them. The electrons, the valence electrons, shield the hydrogen from the full effect of the magnetic field, right? So what does a chlorine do? It sucks those electrons away, and thus, right? And if the Cl is pulling the electrons away from the CH, well, then there's fewer electrons around the H and less shielding, or you could say deshielding, right? Deshielding by an electronegative atom. This is a really cool, easy way to explain it. And where did we say that a CH next to a Cl is going to be? I just said it on the chart. So the CH next to an electronegative atom was 3 to 4, like somebody said, yeah, 3 to 4. So the chlorine's pulling the valence electrons away and turning, and in turn, from the proton. Thus, the proton appears deshielded, it appears to the left. And 3 to 4 is, you know, reasonably to the left of, like, if there's no Cl, it's probably going to be around 1 or 2, you know? Okay. So this shows that for a couple different atoms, and it's kind of like the effect of, like, one of these atoms on a carbon, like a CH3. If we look at, like, and there's an electronegativity measurement here, and so if we think of, like, full fluorine, that's like kind of very electronegative. Oxygen's a little less electronegative. Chlorine's a little less electronegative. Bromine's less. Iodine's actually less electronegative, etc. And you can see the effect of electronegativity on the chemical shift. Very cool. It's almost linear, right? It's almost like a linear effect, which is pretty hard to see in organic chemistry. You don't see this kind of beautiful effect that often, okay? So that fluorine, fluoromethane, is the most deshielded. Okay, that's nice. Then the halogens we see a lot are like fluorine, chlorine, bromine. Those are in the kind of in the 3 to 4 range. Of course, 2.8 is, you know, it's not in the 3 to 4 range, but again, that chart is a little, you know, overly simplified. We generally just say 3 to 4. So 2.8 is almost 3, right? Okay, good. All right, and this is also kind of cool. What if we have 1 chlorine versus 2 chlorines versus 3 chlorines? Well, that effect is kind of additive. Sorry, I did it backwards. 3 chlorines versus 2 chlorines versus 1 chlorine. Well, there's an additive effect, right? 7 to 5 to 3. Of course, these go off that chart. So that chart is that chart is a little, you know, it's not perfect because it's not showing like 3 chlorines and 2 chlorines. Usually we don't have that situation. But of course, this makes sense that if you have multiple chlorines, you have multiple electronegative atoms, you have more of an effect. It's like an additive effect, right? So the effect increases with a greater number of electronegative atoms. Makes sense, right? What if I have a CH2Br versus CH2CH2Br versus CH2CH2CH2Br? Well, and I'm just showing where the red protons are. It's cool that this is the effect dissipates. The effect dissipates as you go further away. So the effect is felt a couple atoms away. It's just not as severe, right? The one directly connected is 3.3, and then 2 atoms away, it's 1.6, and then 3 atoms, you know, the effect's last is around 1.25. So the effect decreases with increasing distance. Makes sense, right? So that's pretty cool. Okay, so a couple examples. This is just a simple molecule. What's the name of this functional group? Begins with E. Don't say ester. End of organic 1. Yeah, ether, yeah. Methyl tributal ether. Very boring molecule. And the NMR is very boring also. But look at does the integration make sense? 3 to 9? That should make sense to you, right? Of course. That's the CH3, it's 3. That's 3 CH3s, that's 9. Yeah, that makes sense, right? What about the chemical shifts? Do they make sense to you? The CH3 is next to oxygen. And where's it come? 3 ppm. Does 3 ppm match this chart? 3 ppm. What comes around the 3 to 4 range? A CH where a carbon is directly attached to a electronegative atom. Yeah, oxygen's electronegative. The CH3 is next to the oxygen. Yep, 3. That totally makes sense. This is a very boring 3CH3 terp-butyl group. And it's just at 1. Why is that? I mean, there's an oxygen nearby. Well, that oxygen is kind of far away. It's not directly connected to the CH3s. So these 3 CH3s are really connected to this carbon in the middle. So that's why they don't really feel the effect of the oxygen very much. So they're 1 ppm is kind of the sort of default aliphatic region. Okay. Okay, so this molecule, I just kind of picked some random molecules to kind of show this effect. Well, we got, you know, 3 chlorines here, 2 chlorines on this side, 1 chlorine on this side. Did the integrations make sense? 1 to 2 to 6. So the carbon shields the effect of the oxygen. That's on the last one. Yeah, somebody said, does the carbon shield the effect of the oxygen? Let's go back. Yeah, a little, yeah, enough. Yes, basically, yeah. Yeah, the oxygen is separate. You know, these carbons can very minimally see that oxygen. It's kind of far away because this carbon shields them. All right. Okay, but this one, this is the first thing about the integration. 1 to 2 to 6. Does that make sense? 1 to 2 to 6. Well, and I mean, we have 3 kinds of protons. We have this proton. We have these protons, the CH2, and we have the 2 methyls. Yeah, 1 to 2 to 6 makes sense. 1 to 2 to 6. So we know which of these signals is which just from that, just from the integration, right? But what about chemical shift? Like this carbon has how many chlorines on it? The CH. Oh, it's got 2. So it's kind of like a double effect, right? That's why it's additive. And is that 5 to 6? You know, which is weird because that would probably be where the alkenes come. But again, that just shows that this table is not perfect, because if you have a weird situation of like 2 chlorines, then this table is not going to work, right? So for the most part in this course, this table is going to be, you know, pretty dead on. But anyway, yeah, 2 chlorines is a little further than 1 chlorine, which is in the 3.7. Well, that's perfectly right there, so that makes sense. And then these are the 2 boring methyl groups that are kind of far away from those chlorines, and they're at 1-ish, right? That's pretty cool. Okay. Why does deshielding occur? One other reason. Why do aromatic protons get deshielded? And they're further, right? 7 to 8 ppm, right? 7 to 8 ppm. Well, this has a different explanation because that's like especially far, and it looks a little funny, but it's kind of cool. So that what's going on here? This is called a ring current diagram. What this is showing is that if you have a benzene, you have a magnetic field. You have a magnetic field, and then the electrons make these little ring currents of the electrons, the pi electrons of the benzene. And so the ring, and basically what happens is the electrons kind of create an opposing magnetic field in the middle. Okay, so there's an opposing magnetic field in the middle of benzene. And what did we say about opposing magnetic fields? We said an opposing magnetic field is shielding, right? Right. So right in the middle of the benzene is a shielding effect. Shielding. And where did the shielded protons come? On the left or right? Shielded protons come on the left or right?
Right.
On the right. Okay. But there's no protons in the middle of the benzene, right? Where are the protons on a benzene? They're on the outside, right? So this is really cool. The electrons there's an opposing magnetic field in the middle where there are no protons. And then it kind of wraps around and creates a almost additive magnetic field, an additive magnetic field, which is deshielded, extensively deshielded. That's why these protons on a benzene come at like 7 ppm, because they're extensively deshielded. In the middle is a shielding effect, and it wraps around, and on the outside is a deshielding effect. And that's why benzene protons come at 7 or 8 ppm. Okay, this is going to be fun. When we get a couple more chapters down the road, you're going to see a molecule, a huge aromatic molecule. It has like 14 carbons, like a huge, big ring, a big ring, big aromatic ring with protons in the middle. Right? Where are those going to be shielded or deshielded? It's going to be imagine a big benzene with protons in the middle. They're going to be shielded, and they're so shielded that they're like -3 ppm. They're off the scale because it's such a weird thing. You can Google it if you want. I think it's called. Let me see. Let me find it. Maybe I can share it. 18 annuline and I can't type. 18 and there it is. Yeah, look at this weird. This is a weird molecule that is aromatic in the same way that benzene is. We'll talk about that in the aromaticity chapter. But there's protons in the middle. There's protons, right? There's a bunch of protons, and they're all extensively shielded. And what about the protons on the outside? They are extensively deshielded. Somebody said, is this similar to 18 crown 6? Not really. This is a little different. 18 crown 6 is a ether, so there's a bunch of oxygens. It's a macrocycle. It's a big ring, but it's different, a little different than 18 crown 6. Okay, yeah, isn't that cool? Okay. All right, so we're cool with that. Now you kind of understand why benzene is so deshielded. Aromatic compounds come at 7 or 8 reliably. Okay, so this is a boring molecule called toluene or methylbenzene. First of all, does the integration make sense? 5 to 3. Does that make sense? Yeah, of course. 5 protons on the aromatic ring, 3 protons on the methyl. And the chemical shift, does that match my table up here? Yep, right in the middle. 7 ppm is the benzene. Methyl. Now, what about methyl? Which bracket is methyl in? It's next to a pi bond, right? These are pi bonds, right? The benzene is a bunch of pi bonds. So CH next to a pi bond, yeah, that's 2 to 3. And where is it? It's right in the middle of 2 to 3. So this is a great example of a benzene and CH next to pi bond. Okay, we're done with this lecture. Now we're on to number 3. The third one, whatever I call it. Whoops. All right, I guess the third one. Recognizing equivalent protons by Proton Nmr. All right, so in general, chemically equivalent protons have the same chemical shift. So that means like protons that have the exact same environment in a molecule have the same chemical shift. Chemically non-equivalent protons often have different chemical shifts, not always. Thus, NMR easily tells you the number of different types of protons. We already mentioned that. It's the first thing I probably told you. So this molecule, how many types of protons are there? Just looking at the molecule. You kind of got like the outside ones, which are symmetrical, and the inside one. So you might say there's two, A and B, two sets of non-equivalent protons. What about this one? 1-bromopropane. Well, it looks like 3. You might be seeing a pattern. 1 or 2, 3, 4. No, I'm sorry, 2, 3. Next one will be 4. Okay, so what about this one? So let's just go left to right. All right, so we have like the 3 CH3s, that's 1. We have a CH, that's 2. A CH2 is 3, and then the CH3 is 4. Now this CH3 is different than these CH3s because this CH3 is next to a CH. These 3 CH3s are next to a non-CH, just a carbon. So this is 4. A, B, C, and D, all right? What about this substitute benzene? Well, I can say, well, there's going to be 1, 2. Now there's symmetry here, so this is going to be like 3, 4, and 5. All right, because this is a symmetrical benzene. A, B, C, D, E. You may have heard this before. This is called parabenzene, P-A-R-A. There's 3 of them. There's ortho, meta, and para. We'll see that more in the aromatic chapter. But it's called para. Okay, so we got 5 sets now. What about this molecule? This is meta. Meta is when you have 2 things that are separated by one carbon. Well, we got 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. All right, so this is cool. One of the nice things about Proton Nmr is it'll quickly tell you at least, how many unique types of protons you have. One other little tidbit about this. Cyclohexane is kind of weird because cyclohexane, it's just a bunch of CH2s, right? But they're in a chair conformation. You might think that, well, I got 6 CH2s that are exactly the same, that you just get a single signal in the NMR, and you actually do. At 25 degrees Celsius, this is going very rapidly, this chair flipping business, and you get a singlet at 1.36 ppm. But interestingly, one of the cool things about NMR is you can actually reduce the temperature like massively, like negative 100 degrees Celsius. We can go really low temperatures. If you do that, it kind of freezes these 2 out, and they actually do have slightly different chemical shifts, which is just a kind of little trivia point in NMR. So at our negative 90 degrees Celsius, the conformations are frozen out, and then we get actually 2 different protons, the axial and the equatorial. Somebody raised a hand. Let's see.
I just had a question about the previous slide.
Yeah, let me go back.
With the examples at the bottom. Yeah. So for that last one, how is it 6 different ones? Like, how is B and E not the same?
B and which?
B and E. Oh, actually, never mind. I see.
Yeah, so, the E is totally in between 2 different things.
Yeah.
The C, D, E is in between 2 things. B, C, and D are totally different. They're, one's next to a CH3, one's in the middle. D is next to the OCH3. So yeah, they're different.
Okay, yeah, I saw it. After I looked at it again, I was like, okay, thank you.
Cool. All right. So yeah, you can do this thing called low temperature NMR, which is sort of cool. And if you have things that are equilibrating like this will freeze them out, and you actually see the signals independently of each other. Kind of cool. Okay, so now let's move to the third topic. We talked about integration, we talked about chemical shift. Now let's talk about splitting or spin-spin splitting, all right? So let's first show a simple example of it, or let's first mention what are the types of splitting. Often a group of hydrogens will appear as a multiplet rather than a single peak. Multiplets are named as follows: singlet, doublet, triplet, quartet, quintet, or sometimes called pentet, sextet, or sometimes called hextet, sextet or hextet. 7 is called a septet. We have 8, there's the octet. 9 is nonet. This happens because of interactions with the neighboring hydrogens. So we haven't talked about neighboring hydrogens yet. Now we're going to talk about that. And it's this concept called spin-spin splitting. Okay, so here's a simple example. 1,1,2 trichloroethane. We got a carbon on the left with 2 chlorines. We got a carbon on the right with 1 chlorine and 2 hydrogens. First, if you think about just the chemical shift of those two, well, the integration first. Integration totally makes sense. 1 and 2, right? 1 proton, 2 protons. What about chemical shift? Well, I have a peak at around 5, almost 6. Well, that's probably the CH next to 2 chlorines, because the chlorines are additive, right? The other one's just at 4. That makes sense. It's just a CH2 next to a single chlorine, so that makes sense. But what about this splitting phenomenon? There's a triplet, and a doublet. Okay, so let me just we'll just explain why is it doing that. Why is this a triplet and why is this a doublet? These multiplets are due to the spin-spin splitting and are predicted by the n plus 1 rule. That's gonna be a new thing we have to learn. The n plus 1 rule. Okay, so well, if we look at the CH, we've decided this left peak's a CH, right, with the 2 chlorines. How many neighboring protons are there? Well, there's 2 neighboring protons, right? What's 2 plus 1? So 2 plus 1 is 3, and that is why it's a triplet. In a nutshell, left peak is a triplet because there are 2 plus 1 neighbors. You count the neighbors and add 1, all right? So that is a triplet. Now what about the CH2? How many neighboring protons are on the CH2? So there's how many neighboring protons? There's 1 neighboring proton. What's 1 plus 1? That's 2. And that's what this n plus 1 rule is. It's the neighbors plus 1, all right? So the CH2 has 1 neighbor, and that's why it becomes a doublet. Okay, that's the rule in a nutshell. Okay, we'll see lots of examples. What if you have 6 neighbors?
Sorry, can you repeat that again?
Yeah. So in a nutshell, the way you predict the splitting, like there's a triplet here, the splitting of and this is the CH, right? This is the CH, is the number of neighbors plus 1, right? So the CH has how many neighbors? Oh, it has 2 neighbors. 2 plus 1 is 3, which is a triplet. On the other one, the CH2, we know it's a CH2, the integration and the chemical shift, yeah, it has 1 neighbor. So 1 plus 1 is 2, thus it's a doublet. That's the rule. What if I have like 6 neighbors? 6 neighbors. It's a CH with CH3s on both sides. 6 neighbors. What's the splitting of that CH going to be? What's the name of it? Somebody say it. It was a septet. So that would be like 7 little peaks. We'll see that in a second also. So 6 neighbors would be a septet, right? It's the number of neighbors plus 1. Okay. So this is that, we already basically just explained the n plus 1 rule. This is the number of neighbors plus 1. So where do the multiples come from? Interaction with the neighbors, right? And this kind of shows it also. Okay, so this CH has 2 neighbors, right? 2 neighbors plus 1 becomes a triplet. The CH was a triplet because there's 2 neighbors plus 1. All right, this CH2 has 1 neighbor. What's 1 plus 1? 1 plus 1 is 2. It's a doublet. All right, and these are the names of those multiplets again. Like I said, like septet is if you have 6 neighbors plus 1 would be a septet, which is 7 little peaks. 7 little peaks. We'll see lots of examples of all these in a second. Okay, so a couple cases where the n plus 1 rule does not work. One is if you have like a pair of CHs, we'll say, and they have identical X and Y groups, so there's like no difference at all. If that's the case, these will just come at the same place, and if that's the case, they won't split each other. All right, so there's no splitting. Same with this. If I say I have a CH2 and a CH2, and we'll put like if X and Y are the same, like chlorines on both sides, no splitting. They won't see each other. They would just be a single peak, and it'd be a singlet. Okay. Generally speaking, like if I have a CH3 group or something, those don't split each other either. The CH3, I mean, those are obviously not neighbors. Those aren't neighbors. When you count the neighbors, it's on the neighboring carbon, right? So, and generally speaking, also CH2, these protons don't split each other. Okay. All right. More exceptions. Well, these are actually rules where they do apply. Like if I have a chain of like CH2, 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 CH3, yeah, n plus 1 rule will apply on these atoms. And also like on this cyclohexane, like, you know, that's CH3. What is it going to be? How many neighbors on this are next to the CH3? 1. So it should be a doublet, right? The CH3 should be a doublet. This might, you know, this CH is going to be kind of complicated because it sees 2 plus 2 is 4 plus 3. 4 plus 3 is 7, so it should be maybe an octet, like eight little peaks. Okay, right? This neighbors plus 1. So you count the neighbors, add 1. Alkenes are a little funny. We'll show alkenes in a bit. And also, benzenes are a little funny, but there are definitely cases where benzenes do show signals. Like if I have a substituent on here, like a chlorine or something, then the n plus 1 rule does apply. Okay, but let's keep going. Okay, common splitting patterns. This is a nice thing to think about. Okay, so if I just have a pair of CHs and X and Y are different, what's the splitting pattern going to be? Well, both of them have one neighbor. What's 1 plus 1? Doublet and doublet. So these should be, you know, if you have a pair of CHs with different things on them, they should be a pair of doublets. What about a CH2 and a CH? Well, we just saw this situation. It would be a doublet and a triplet, right? A doublet and a triplet. Because the CH2 sees one neighbor, it should be a doublet, and the CH sees 2 neighbors. 2 plus 1 is 3, it's triplet. What about a pair of CH2s with different X and Y groups? What should you see? A pair of triplets, right? That makes sense? A pair of triplets, because both cases, 2 neighbors plus 1, 2 neighbors plus 1. What about, this is like a CH next to a CH3. Well, what about the CH, we'll say is the one on the left here. How many neighbors are next to the CH? 3. 3 plus 1 is 4, it's a quartet. This CH3, though, looks back and it says, well, I see one neighbor. 1 plus 1 is 2, it's a doublet. What about a ethyl group, CH2 next to CH3? This one is very common. And so ethyl groups, we're going to see lots of ethyl groups in our NMR spectra. And it's a quartet next to a triplet. So very often, if you see a quartet and you see a triplet, you're like, there's an ethyl group, right? All right. Quartet next to a triplet. And what about, what's this called? Organic 1 nomenclature, something propyl. Anybody remember? What kind of propyl group is this? It's a something. It's one of the branched propyl groups. Iso, somebody said. Yeah, isopropyl. Okay, so how many neighbors are on the middle CH? Well, there's 3 here, 3 there. 6 plus 1 is a septet. So that's a nice septet, right? 1, 2, 3, 4, 5, 6, 7 little peaks. And what about the the methyl groups? They're identical. The methyl groups are identical, so they come at the same place, and they see that central CH, so they're a big doublet. So how do you distinguish an ethyl group from an isopropyl group? Ethyl group is a quartet and a triplet. An isopropyl group is a septet next to a doublet, right? Okay. Okay, a little bit of benzenes. Para-disubstituted. Those are where you got two things on opposite sides. That is recognized by a pair of doublets in the aromatic region. Where's the aromatic region again? 7 to 8, right? We just remember that. 7 to 8 is the aromatic region. Why a pair of doublets? All right, so if I have X and Y are different, why would I have a pair of doublets? Well, there's symmetry. So these protons are identical. These protons are identical. And, well, in these two protons, you know, in both cases, they basically see the neighbor, right? There's one neighbor, and that's why they become a doublet. These protons, they both see their neighbors, and there's, you know, essentially one neighbor next to each of these, and that counts as a doublet. So you get a pair of doublets, right? So how do you, if you see a benzene and you see a pair of doublets in the NMR spectrum, you say, is it para or ortho or meta? You're like, oh, it's para, because para, which is this is para, right? Para disubstituted. What does disubstituted mean? Disubstituted. That means two things, right? So there's two X and Y, right? Two different things. Para disubstituted benzenes have para disubstituted benzenes will be a pair of doublets. And somebody says, why is the first one only a doublet if is this the same example? Why is the first one a doublet if they can't have so if we're assuming they have two different groups, like a chlorine and like a nitro or something, or a methyl or something. And because if they're the same, there's this perfectly symmetric, and these will not come at different places, right? So this kind of requires X and Y to be different, right? And somebody said symmetrical ones can't do splitting. That's correct, yeah. Okay, so here's a real example: chloronitrobenzene, right? Look at that, two doublets, and they come in different places, roughly in that 7 to 8-ish region, right? Cool. What about ortho and meta? Those are the ortho was like directly next door. Meta was one away. And what's cool about this is they all have a kind of their own little trick to you know what they look like. Ortho's next door. So this is like sorry, this is meta. This one's meta here, meta. So it's nitro and a trifluoromethyl. Okay, so what are the splittings? We have, what's this one? Kind of like a singlet, two doublets and a triplet, right? A singlet, two doublets and a triplet. Does that kind of make sense? Like, which would be the singlet? If we're just looking at the aromatic region, the singlet, how many neighbors are next to a singlet? How many neighbors are next to a singlet? Well, if it's a singlet, there's no neighbors, right? There's no neighbors if it's next to a singlet. So which of the CHs would the singlet be? Maybe the one where there's no neighbors, like right there, right? That's a CH with no neighbors, and thus it'll be a singlet. And then you got two doublets. Why do we have two doublets? Oh, because that's a CH, that's a CH. They're both doublets because they have one neighbor. And there's the neighbor. And how many neighbors does this central CH have? Two. Two neighbors plus one becomes a triplet, right? So that's pretty cool. How do you know if you got a meta benzene? Because you got a singlet, two doublets, and a triplet. That's why, right? Okay, and what about ortho? This is bromo-trifluoromethoxybenzene. Well, what are the signals you're going to see for an ortho? Well, of course, I have two doublets because they only have one neighbor, and two triplets, right? Two triplets, two doublets, two triplets. Singlet says Singlet has singlet, 2 doublets, and a triplet. I think what you meant was meta. Meta, I'm looking at the chat. Meta, this is meta on the left. Meta has a singlet, 2 doublets, and a triplet. Ortho is the one on the right. Ortho will always have 2 doublets and 2 triplets. It's pretty cool. So this one's called meta, this one's called ortho. What's the other one we just did on the last page was para, P-A-R-A. All right, good. So that's one cool thing we can do already is if, you know, and we're not even really assigning which of these protons is which. All we're saying is it ortho, is it meta, or is it para? And we can do that simply by looking at the splitting. Is it ortho, is it meta, or is it para? Okay. The chemical shifts vary with the substituents. So we're not really caring about, like, you know, which of these doublets is which. Well, we don't really care. We figured out it's meta, so that's fine, right? In this one, we have 2 doublets and 2 triplets. Which is, you know, which doublets and which triplets are the atoms here? That's something we don't really care, and it's not very easy to figure out. So we're going to kind of skip that detail, the chemical shift detail. The splitting detail is pretty easy to interpret. Okay, so chemical shift again is the position on the x-axis. All right, let's show some examples now with splitting. Okay, so this is ethyl bromoethane. These are, you know, we're talking about old, obsolete NMR machines. This is 60 megahertz, so this is really old, but it still shows the key stuff, right? Well, we have a CH2 and a CH3, which is which, based on chemical shift. Well, the bromine's probably the CH2 at 3.5, and then the methyl is the other one, you know, 1.7. But what splitting do we have? A quartet and a triplet. What do we say about ethyl groups? Quartet and triplet, right? And why do we have a quartet and a triplet? The CH2 has how many neighbors? It has 3 neighbors. 3 plus 1 is 4. It's a quartet. CH3 has 2 neighbors. 2 plus 1 is a triplet. Okay. What's this funny peak at 0? Anybody remember? Funny peak at 0. 3 letters. T something something. TMS, tetramethylsilane. So it's a silicon with 4 methyls on it, and that's very shielded. And shielded means to the right. The peak at 7 is the solvent, the chloroform. I think they're using for this. Okay, good. Nitropropane, 2 nitropropane. So the nitro is very electron withdrawing, makes de-shielded CH peak. Well, this is a nice isopropyl group. That's an isopropyl, right? Like we said. So this peak, this multiplet is what's the splitting of it? You can try to count them, or you can say, well, from the structure, it should be a what? 6 plus 1. 6 plus 1 is a something tet. 6 plus 1 is 7. Septet. That's a septet. And if you count really carefully, you'll see 7 peaks. 1, 2, 3, 4, 5, 6, 7. Okay. What about this big doublet? That's the pair of CH3s. Okay. Acetaldehyde. Okay, so first of all, aldehyde is far on our left of our chart. If you look in the chart, it was like 9-ish, I think. That's off the scale here, but that's right. That's over here. This is the aldehyde, the CH of the aldehyde, and it is a what? It looks like it's a quartet, right? It's a quartet. And why would it be a quartet? Why would the aldehyde be a quartet? Because how many neighbors are next to the aldehyde? 3. 3 plus 1, 4. So you see a quartet, 4 peaks. Whereas the CH3 has how many neighbors? The CH3 has 1 neighbor. 1 plus 1, 2. It's a doublet. Okay? Now that just shows the splitting more clearly. Another little thing. The intensities of the peaks follow Pascal's triangle, which you may have seen, I don't know, maybe in an old math class or something. Pascal's triangle is just kind of a little mathematic arrangement where you see, like, as you make a little triangle, anything underneath is the sum of its parents. So 2 is the sum of 1 and 1. 3 is the sum of 1 and 2. 3 is the sum of 1 and 2. What this is showing is the intensity of the multiple peaks kind of follows Pascal's triangle. We'll see why in a second. But this isn't really a big deal. It's just you'll notice this. When you look at the intensity of the peaks, they kind of follow this arrangement. And there's an easy explanation for this that we'll see in a second. Like a quartet is 1 to 3 to 3 to 1. So it's like small peak, big peak, big peak, small peak. Okay? Okay, so why does it happen? Why do we have the n+1 rule? Why do we count the neighbors and add 1? This is cool. It's a kind of a theoretical discussion. It's not that bad though. Not too critical that you don't have to like learn like this theory, and I'm not going to test you on the theory, but just follow it as best as you can. Okay, so if I consider proton HA and it has a neighbor and it becomes a doublet, it's due to the spin of its neighbors. So let's think about HA. HA here. It is a doublet, right? HA is a doublet. Why is it a doublet? Okay, so what happens is this. HA has a neighbor, and that neighbor can either be aligned with a magnetic field or disaligned with a magnetic field. And what that does is it splits HA into the aligned and the disaligned will kind of create a very tiny, tiny, tiny shielding and deshielding effect. And thus, HA will have two components to it. One that's a little bit aligned and one that's a little bit disaligned. Okay, so that's kind of why a doublet's a doublet. Why one neighbor? Because the magnetic field of the neighbor will subtly affect the chemical shift of HA. All right. So what about like triplets and things like that? It's the same exact thing. All right. So here we have that's the same exact thing. So this is a CH next to a CH. So this CH has one neighbor and one leg of the doublet's aligned, the other leg is disaligned. What if we look at the other CH? Oh, it's the same exact thing. One line is aligned and the other is disaligned. All right, so we basically get a pair of doublets. Okay, let's keep going now. CH next to a CH2. This gets a little weird, all right? So this CH sees a CH2. And how many atoms are on that CH2? Well, NMR visible atoms. 2, right? There's 2 protons. Okay. And since there's 2 protons, there's a couple different spin states. They can be both aligned, so aligned, aligned, and that's the leftmost peak. Or they can be aligned and disaligned, or they can be disaligned and aligned. And these kind of will come at the same place. As such, this is kind of like a larger peak in the middle, because it's like represented by 2 different sets of spin states. Isn't that weird? Kind of cool. What about the one on the right? This is the disaligned, disaligned. So it's 2 hydrogens next door, and they're disaligned and disaligned. That's why it's a triplet. What if we look at the CH2 now? How many neighbors does the CH2 have? Well, it has 1 neighbor. So then it's just looking back and it sees a CH, and it's just a doublet, right? Same exact thing. So now we'll go a step further. CH2 next to a CH3, like an ethyl group, right? Looks a little funny, but it's really not that crazy. All right, so CH2 next to a CH3. So the CH2, how many neighbors are there? There's 3, right? And they can be aligned, 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 and that's the left peak of the quartet. Or they can be disaligned, aligned, aligned. Or they can be aligned, disaligned, aligned. Or they can be aligned, aligned, disaligned. So there's like 3 different states, right, of those 3 CHs, right? And that's the left big leg. And then we go to the next one, and now this one's aligned, disaligned, 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 aligned, disaligned, or disaligned, disaligned, aligned, and that's the 3rd peak, the other large leg. And then lastly, the furthest right spin state is disaligned, 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 and that's the 4th leg. All right, that's how a quartet. That's why a quartet is formed. That's like the theory of it. And again, you don't have to like memorize this. I'm not going to test you on this, but you need to know the n+1 rule. But this is why multiplets appear as they do. Kind of cool. Okay, so what about the CH3? Well, it looks back and sees a CH2, and it's just aligned, 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 disaligned, disaligned, aligned, and disaligned, disaligned. So It's the same kind of thing. That's why we end up getting a quartet and a triplet. It's pretty cool, I think. I mean, but it's a little weird to think about this and the neighboring spin states. Okay, coupling constant. We're almost at the end of this. At the end of coupling now. Coupling constant. What's this coupling constant? It's related to splitting, right? It's this concept of splitting that we're talking about. So it's really just the distance between the legs of a multiplet. So a quartet, it's the distance between the legs. It's measured in hertz though, because normally, x-axis, we think about the position on the x-axis. We say, oh, it's in ppm, right? We have the hertz. We can also convert back to hertz. The J value is always measured in hertz, so we have to kind of like reverse compute it. You're not going to have to do that in this class. You may have to do that in the lab class, though. So you'll see some J values in the Organic 2 lab. But it's really just the distance between the peaks, all right? So okay, and it's yes, the measured in hertz, peaks, the distance between the peaks and the multiplet. Okay. Okay, so this is. And since it's measured in hertz, it's interesting that hertz, the meaning of hertz varies with the NMR instrument. So this is an old 100 megahertz NMR, right? Coupling constants are constant. They're constants are constants, right? They do not change with the strength of NMR. So if I use a better NMR, we'll just say, get an extra $200,000. We buy a 200 megahertz NMR. It's still 7.5 hertz. The hertz, by ppm these are different, but the distances are still 7.5 is the same. So what do we say? Which is the better NMR machine here? The top or the bottom? Probably the bottom one. It's a better. You get better resolution. That's what you get if you spend an extra $200,000. These are very expensive NMRs, right? Okay, so why would we buy that? At SF State, one of our NMRs is $500,000, right? Why do we pay for fancy and expensive NMR machines? Because you get better and more resolution. So 50 megahertz, this looks like a mess. 100 megahertz still looks like a mess. 200 megahertz, you can start seeing a triplet, a quartet, and a triplet, right? Because it's the result. At UCSF, I got to work with like a 900 megahertz NMR. It's a huge, huge, huge thing. You have to climb up a ladder to get to the top of it. And it's a 900 megahertz NMR, and it gave you super, super resolution. Somebody said, what's the highest? I think it's around 900. I think 900 is actually up there, maybe 1,000. Somebody said at my house. All right. So somebody's got an NMR at their house. All right. But anyway, that's why we buy expensive machines. All right. Okay, what's the meaning? Just in a nutshell, we're very minimal. The default is usually about 7. 7 hertz is kind of a default one. But sometimes with alkenes, you can actually see like the geometrical differences of alkenes. Like a trans alkene is actually kind of a high hertz. Cis is actually usually a very small number. So 15 is, I think that might be wrong. I think it's usually around maybe 6 to 10. But anyway, I mean, like if I need to distinguish a trans alkene from a cis alkene, it's pretty easy with the J value. Okay, I think this might be a typo actually. I should double check that. But usually cis ends at around 10. And then axial and equatorial protons, they often can be distinguished also. So it's like you can get some geometrical information from J values. Okay. All right, overview of Proton Nmr. Each different type of proton has a peak or group of peaks, right? And that could be a multiplet, like a doublet or a triplet. Each different type of hydrogen. The chemical shift gives a clue as to the type of hydrogen. Is it an alkane? Is it an alkene? Is it a benzene? Is it an aldehyde? Is it next to a chlorine? Is it next to a pi bond, right? That's the chemical shift. The little chart really saves you there, yeah? The integral tells you the relative number of hydrogens of each hydrogen, the relative number of each type of hydrogen. right? Integral. If it's a 2, it's like maybe it's a CH2, right? If it's 3, it's maybe a CH3. Spin-spin splitting gives you the number of hydrogens on adjacent carbons, right? It's an n+1 rule, n+1. And then coupling constant often gives you information about the stereochemistry. You know, cis and trans alkenes are a good example of that. Cis and trans alkenes. Okay. Next. Okay, so we're all experts at Proton Nmr now, kind of. Let's just show some examples. Some more examples. We've seen a couple examples, but this is a methyl ethyl ketone. Well, you got a ketone in the middle, you got a methyl group and an ethyl group, right? You can see the ethyl is the quartet triplet pattern, and you got the methyl group. How many neighbors are next to methyl? 0. There's no neighbors next to methyl. 0 + 1 is a singlet, right? What about the chemical shift? Well, that makes sense too. Remember, next to pi bond, what do we say next to pi bond is around 2 to 3. Where are the CH3 and that CH2? 2 to 3. Perfect. This is a boring CH3. It's out at 1. Okay. Ethyl acetate. Well, this is actually funny because this one looks very similar to the last one. Look at methyl ethyl ketone versus ethyl acetate, which is an ester. It's very similar, except the big difference is now that CH2 is dragged down to 4. Why is it at 4? Anybody know why the CH2 got dragged down to 4 ppm? Maybe because it's next to the oxygen, right? Electronegative atoms drag things down to that 3 to 4 region, right? Cool. Alpha chloropropionic acid. So it's a carboxylic acid. A carboxylic acid. It's got a CH3, a CH, and a Cl. Still not that exciting. Let's look on the far right. Around under 2 ppm is it looks like a CH3 by integration. It's a doublet. Why is it a doublet? Why is the CH3 a doublet? Because how many neighbors are next to the CH3? Oh, 1. Oh yeah, 1 + 1 doublet, triplet. It becomes a doublet. I'm sorry, doublet. And then this CH is probably this one, and it's a quartet. Why is it a quartet? Because there's 3 neighbors. 3 + 1 is a quartet. Why is it at 4.5? It's a little far down there, de-shielded. And that's because it actually has a double effect. It's next to the carboxylic acid, which has a little bit of an effect. It's next to the chlorine, which has a huge effect. Okay. Now, what about this peak way, way, way downfield? 1. What's that one? 12 ppm. Huge downfield effect. Which proton did we not discuss? The carboxylic acid. Yeah, that's right. So carboxylic acids come way, way, way down, 10 to 12 ppm. Okay. Yeah. Okay. Cool. Tributal methyl ketone. So this is another ketone. Very boring molecule. So we have a ketone in the middle. Doesn't have much of an effect, but it does. You know, the methyl will feel that effect a little bit, and that is, you know, is next to a pi bond. So it's around the 2 to 3 range. So it's, you see, it's, you know, a little under 2 in this case, but it definitely feels the effect of the ketone. And then the 3 methyls here they're all both singlets. That's the terbutyl group, 9 protons. Nitropropane. Nitropropane. Well, this is just really a propyl group next to a nitro. A nitro is just an electronegative functional group. 2 to 2 to 3. You can kind of see which is which here. 2 to 2 to 3. There's this downfield one is that CH2. This middle one is here, multiplet. And then we have the triplet over here. So how many neighbors in this middle one? How many neighbors? Well, we see 3 on one side, 2 on the other. 3 + 2 is 5. 5 + 1 is 6. So it's we call it a hextet or sextet, which is 1, 2, 3, 4, 5, 6 little peaks here. And of course, the CH3 and the CH2, they both see 2 neighbors. 2 + 1 is 3. They're triplets. Okay. Dichloropropane. 1,3-dichloropropane. Well, so in this case, in this case, you have like, how many unique types of protons are there? Well, we got the outer ones and the middle ones, so that's 2. And the outer ones will integrate to 4, and they will be a triplet because there's 2 neighbors. And then the inner one has how many neighbors? 4 plus 1, 5 is a pentet. 1, 2, 3, 4, 5. Chemical shift totally makes sense. Like these CH2s next to chlorines are in the 3 to 4 range, which we've seen a little bit now. This one's, you know, in the 2 to 3 range, which is a little weird, and that's because this CH2 actually does feel the effect of the chlorines in the distance a little bit. 2 chlorines in the distance will shift this CH2, you know, to like 2.2, because electronegative atom effects can travel through a couple atoms. Benzoyl alcohol, this one's an interesting one. Okay, so the thing that integrates to 5, that is around 7 to 8 ppm, what is that? 5 protons, what do you guys think? The benzene, 1, 2, 3, 4, 5. So that's the 5 protons of the benzene. Then we have something that integrates to 2, that's around, you know, it's pretty far, it's far downfield. What's that? 2 protons. And it's a singlet. It's the CH2. It's downfield because of the oxygen, and also the benzene. It's like a double effect. Sees the benzene, sees the oxygen. So it's actually kind of off our little scale too. It's, you know, it's beyond the 3 to 4 region, and that's because of the double effect. And what's this other one? This is the OH. This is the OH here, and this is an important thing that I haven't mentioned yet. If you have an OH or a carboxylic acid, we'll say OH. Generally OHs, maybe NHs. If you add D2O, what's D2O? It's like water. It's like water, but it's not H2O, it's D2O. D2O is deuterium oxide. It's like, we call it heavy water. It's a higher isotope of proton, right? Of hydrogen. And Proton Nmr, which is what we're talking about, Proton Nmr does not see deuteriums, right? So if I add D2O, all I do is add 1 drop. Doink, 1 drop into NMR sample. This OH will change to an OD because this is an acidic proton. It'll exchange. The OH becomes an OD. And what happens to an OD? Well, you don't see OD in Proton NMR, so the peak goes away. It disappears. So this will be a useful trick. Sometimes we'll say, oh, this peak disappears with D2O, and that the hint will be, oh, it must be an OH, right? Okay. Here's a ester, slightly complicated ester molecule. By integration, we can pretty much figure most of this out. 5 to 2 to 2 to 3. Well, 5 is the benzene. We got a pair of CH2s. One of them is next to an oxygen. They're both triplets, right? They're totally both triplets because they both have 2 neighbors. 2 plus 1 triplet. 2 plus 1 triplet, right? But which is the downfield one? The 4 point something. Is it the left one or the right one? Left or right CH2? The 4 point something, which is pretty far downfield. Remember, it's more downfield than simply being next to a benzene. If you're next to an oxygen, it's going to be the one at 4 is actually going to be the one on the right because it's next to the oxygen. So this CH2, the left triplet is the right proton here, okay? Because it's next to the oxygen. The oxygen has a huge effect. This has an effect next to benzene, but that effect is not as severe. So this being next to a benzene is not as severe of an effect. And we already said that's usually going to be next to, you know, the 2 to 3 region, right? Next to a benzene. So this CH2 is actually the one on the right. What about the singlet at CH3 thing? Oh, yeah, there it is. There's no neighbors, right? Okay, cool. It's a nice example. Alpha bromobuteric acid. So this is another molecule. Integration, everything kind of makes sense. You got 1 to 1 to 2 to 3. The thing that is at 12 ppm and disappears with D2O is what? The carboxylic acid, right? Okay, the rest of these are very straightforward. 1 to 2 to 3. Of course, the thing at 1 must be a CH, and it's also downfield because of the bromine, and it's a triplet because how many neighbors are there? 2. 2 plus 1 is a triplet. Then you have a CH2 that looks like a kind of a quartet look, and that's actually I think it's a pentet. Yeah, it's at 5 peaks. Why is it a pentet? Because there's 3 plus 1, 4 neighbors. 4 plus 1 is 5. It's a pentet. And of course, the boring old CH3 has 2 neighbors, and it's a triplet. Cool. Just a little bit on alkenes. You're not going to see these really much in the course. I just want to introduce them. For bromobutene. Okay, so where do alkenes come? Remember, they were like the 5 and 6 region. So we have, how many alkene protons are there? There's 3, 1, 2, 3. Okay, so one of these looks like a mess. I call it a forest, a little forest of peaks. And this forest is the one with a bunch of neighbors. It's next to a cis proton, it's next to a trans proton, it's also next to a CH2 proton. And so it is the crazy forest. Okay, then you got what appears to be a big doublet and a small doublet. A big doublet, so maybe large J value, and a small doublet, small J value. Which did we say was the one with the big J value? The cis one or the trans one? Big J value is, I mean, if you just look, the distance, that's the big J value, that's the small J value, right? So the big J value is the trans one, and the small J value is the cis one. So this one, the big difference one, that's the one here on the bottom. The other one is the cis one, because they both have one neighbor, thus they are doublets. Both of these are, they have one neighbor, which is neighboring atom, carbon atom is this one, right? So we just assigned the alkene protons. Yeah, and then we have a CH2, a triplet and a quartet. Well, the triplet is also downfield. It's the one next to the bromine. And then this, why is it a triplet? Because there's 2 neighbors. 2 plus 1 is a triplet. And then this one, how many neighbors are there? There's 2 here, 1 there. 2 plus 1 is 3, and then we add 1 to that. It's quartet. That's why we have the triplet and the quartet. Okay. Trans to butenol. This is a kind of weird molecule. I just want to show as another example. So these 2 alkene protons are total messes. That's why we have the little forest pattern here. And so we can't really distinguish them very easily. Then you have, oh yeah, what the red line? What's the molecular formula here? It's 8. So can we figure out how to add these up and get 8? If these are CHs, it's probably going to be 1 to 1 to 2, because that's a double size of this line, right? 1 to 1 to 2 to 3 to 3, 1 to 1 to 2 to 3, and then this distance looks the same as this, as 1. So it's 1 to 1 to 2 to 3 to 1. Does that add up to 8? 2 plus 2 is 4, plus 3 is 7, plus 1 is 8. So we just figured out, you know, the integrations. 1 to 1 to 2 to 3 to 1. Okay, which one is the OH here? Of all these peaks, the OH must be the one that disappears the D2O, right? And then the CH3 must be this CH3. The 2 alkene protons, we can't really figure out which is which. And then we're left with the CH2 there, the CH2, and that must be next to the oxygen. It's 3 to 4 ppm. One other thing, why is it a doublet? Why is it a doublet? Because there's really technically 2 neighbors. That might be a mystery, right? We have 2 neighbors on this CH2. There's 2 neighbors, right? Should be a triplet. Shouldn't it be a triplet? Well, the thing is that the n+1 rule does not usually work with OHs and things like that. So we don't count this OH with the n+1 rule. It really just sees the CH. So 1 plus 1 is 2. It's a doublet. Okay. I think this might be the last example. Eugenol. This is a real molecule. It's present in clove oil. You may have worked with it in Organic 1 lab. totally smells like cloves. But it's a real molecule. Let's just kind of see the best we can do. All right, so on the far right, we see a CH3 and a CH2 by integration. Where's the CH3? Must be, wow, it's the OCH3 right there. So that's obvious, right? It's a singlet. Why is it a singlet? There's no neighbors. Then we have a nice CH2. Any CH2s here? Oh yeah, well there's that CH2. And of course it's a doublet. Why is it a doublet? Because there's one neighbor, right? Okay, so we assign these two peaks. The 5 to 6 region is what? Benzene or alkenes? The 5 to 6 are benzene or alkenes? They're alkenes, right? So we saw this pattern for that other alkene. So we have the crazy forest. The crazy forest must be the CH in the middle of everything. And then we have the big J value, small J value, the big difference, distance, small distance. Which are those two? You know, the big distance one must be the trans one. The small distance one must be the cis one. Cis versus trans, right? So we just assign these. What disappears at D2O here? The OH. Then we have a weird aromatic that, I don't know, the only thing we can really see is maybe what the singlet is of the above. This is the aromatic region here. Which one of these is the singlet? Top, bottom, left, right. Singlet, no neighbors. Which signal of the aromatic? It's the top, yeah. Top has no neighbors, so it's singlet. And then we have these two doublets. We don't really know which is which, but those are these two ones, right? Okay, so I'm gonna just, we're on to, oh yeah, complex splitting. I'm just gonna introduce this and we're gonna stop because we only have a couple minutes. And I'll go through this again. Complex splitting, where the n+1 rule does not exactly work. This is a kind of a fun little, it's a short lecture too, but I'm just going to introduce it. Okay, so when does the n+1 rule work? When we have like CH2s next to CH2s and all the J values are basically the same, the n+1 rule works great. So here we got a triplet, a pentat. You know, this is a good example of where the n+1 rule works. Okay, everything works beautifully. Count the neighbors plus 1. So what happens when J values are unequal? So say that we have this CH2 and like somehow for some geometrical reason the neighbors have different J values. Then the n+1 rule does not work, and we'll just show an example. This situation, the coupling must be considered independently of each other. So it's kind of weird, and we'll go into more depth next time. But like on the left here, it's a nice triplet, right? Left here, nice triplet. 2 neighbors plus 1 triplet, right? What about the aldehyde here? How many neighbors are next to the aldehyde? Well, there's 2, right? 2 plus 1, it's triplet. These are nice, happy, well-behaved things. The middle one is different, and it sees it sees a doublet in one direction and a triplet in the other, and it becomes this thing called a doublet of triplets. And that's a weird thing, and that's due to different J values. I'll end on this last one. Let's look at this weird molecule. So we have a CH on the left. It's a doublet because there's one neighbor. On the right, we have a CH, and it's a doublet. Why is it a doublet? Because it has one neighbor, right? So the outside ones make sense. But especially with aldehydes, some weird stuff happens. And so essentially the middle peak, the middle CH, will become something called a doublet of doublets. And I'll show that next time. It's pretty cool. This won't be a super in-depth topic. The J values are going to be something that we give. Yeah, they will. We will give you the J values. But let's not worry too much about this yet. And once we see real examples, it'll help. But yeah, I mean, if you need to know it, I will tell you it. Yeah. So anyway, we just wanted to introduce this a bit, and yeah, we're at the end of the day. We got through some cool stuff. There's a lot of topics, but we're actually moving along, and we're gonna. I think the next thing will be carbon NMR. So a little different than Proton Nmr. And then we're going to do the really fun thing of like, here's a spectrum, figure out the molecule. It's a puzzle. It's a really cool puzzle type problem. Okay, I'm going to stop sharing and I'm going to stop record. Well, I'll record in case there's any questions. Any questions? Professor, when will you post the recordings? Okay, so I usually post them the next day. I already posted the first one. It's on my YouTube page. If you look on the iLearn, I have a link to it. It's just a YouTube page. So I usually just post it to YouTube, if that's okay. Some people kind of insist that I put it in iLearn. If you are one of those people, that's fine too. I just think YouTube's really convenient. And there it is. People say, love it on YouTube. Yes, and you can watch cat videos too. Are we cool? Does this kind of make sense, or are you guys still totally confused? I think it'll be cooler once we're solving problems with it. We haven't really solved problems with it yet. Once we solve with the problems, it'll all crystallize and it'll be like, oh wow, this is so cool. So, and if you want to watch ahead, you can always watch last year's video, and you know, over the weekend it might give you a little preview or something. All right. It makes sense, but I feel that I have to review one more time. That's right. Yeah, even watching the videos one more time might help. Remember, the three things are all independent: integration, number of protons; chemical shift, which is the environment of that specific proton; and the splitting, which is the neighbors plus one. They're all completely independent. They're all apples and oranges from each other. There's no relationship between those three topics. So, got to understand integration. You got to understand chemical shift. You got to understand splitting. If you can understand them, everything will be cool. All right. Moving along. Cool. All right, guys. Have a great night.